Alright, so welcome to Module 5. So far we've spent a lot of effort on calculating internal forces and moments in structures, both trusses and frames. These are really important quantities to know when quantifying the strength of a structure, which is one key design criteria. The other key design criteria is serviceability. And that usually refers to the amount of deflections that the structure undergoes when being loaded. Now, we've qualitatively calculated deflective shapes, but now we will introduce a method, the method of virtual work, which can be used to actually quantify these deflections. And this is a very powerful and flexible method, and in fact will be the foundation also for our analysis of indeterminate structures. So we'll spend quite a bit of time elaborating on it and getting accustomed to using it. In this lesson, we'll focus primarily on trusses. So the learning objectives are, first of all, review the basic concepts of work, which are the foundation of the virtual work method. Then we'll describe the principle of virtual work and see how it can be applied to displacement caused by external forces, temperature changes, fabrication errors, and support displacements. And finally, we'll look at some examples of applying the method of virtual work to calculating truss deflections. Now we'll begin our discussion with the principle of conservation of energy. So any external load applied to a structure, like this truss, will produce a set of internal loads. Now we'll often denote external loads using the variable P and internal loads using the variable F with some subscript corresponding to the member. Now we've learned how to calculate these internal loads by assuming that the structure remains rigid, but in reality the structure deforms as its members either elongate or contract. For example, the point B moves to B prime after the load has been applied. So we'll refer to external deformations using the variable big delta, and we'll use subscripts X and Y to denote the direction of the deformation, and we'll use the variable little delta to refer to elongations and contractions. So for example, member 2 is elongated by an amount little delta 2, and member 1 is contracted by an amount little delta 1. And we'll use a negative sign for contraction, positive sign for elongation. Now, if we assume that all work done by the external loads is converted to elastic strain energy, that is, there is no heat loss and no plastic deformation, then the principle of conservation of energy says that the external work and the internal work due to the elongation and contraction of the members should balance out. If you recall, work and energy are analogous concepts. So let's define precisely what we mean by work. So the general formula for work states that work W is equal to the integral of force over a displacement. Now the catch is that that displacement needs to be in the same direction as the force. Let's look at a few special cases. The first one is a constant force over a displacement in the same direction. In this case, work is simply the product of the force times the displacement. Another special case is a constant force with a displacement perpendicular to that force. In that case, work is equal to 0. Okay, so now let's look at work applied to the deformation of a bar like you see here. In this case, the load will not be constant, but due to the physics of the deformation, we'll need to go from 0 to a final value P as the material deforms. In other words, the material behaves like a spring and the deformation is proportional to the load applied. In fact, it is linearly proportional, so the load will need to go from a value of 0 to a value of F, which is equal to P, as it deforms to a length delta. And as we established, the work done by this action is the area under the curve, the force displacement curve. And we'll call, in this case, the work W sub I for internal work, which is another way to refer to this idea of strain energy. And it's pretty easy to calculate the area under the curve as F over 2 times a little delta. We can think of delta in terms of Hooke's law and its relationship to strain. So delta will be equal to the strain of the material times the original length of the material. If we use Hooke's law to substitute in for the strain, we get the stress over Young's modulus times L. And finally, assuming that this bar has a uniform cross-sectional area, we can substitute stress with F over A. So our final expression for internal work is F squared times L over 2 AE. With that definition now, we can apply the principle of conservation of energy or conservation of work to calculating the deflections of an entire truss. So if you recall, we said that by conservation of energy or work, the external work WE done by the 30 kip force applied externally should be equal to the internal work WI done by each of the 3 members of this truss as they deform. The external work is the integral of the external force over the displacement in the direction of the force. So delta X here. And because this is a linearly elastic material, the force increases from 0 to 30 kips as it displaces delta X. So our external work is P times delta X, or 30 kips times delta X. Our internal work, on the other hand, is the sum of the work done by all those member deformations. So we have the sum for J from 1 to 3 of F sub J squared times L over 2 EA. Okay, so for example, F sub 1 would be the plus 50. F sub 2 would be the negative 40. F sub 3 would be the negative 30. But notice that bars in compression still add to the overall sum because that F is squared. All right, so our final equation would be P times delta X, the external work times the external displacement, equal to the sum of all the member forces. And in this case, I'll just make it more general for any truss. by saying M, the total number of members. So this is what we would call the work energy method. And we won't actually use this method very much at all because it's got some pretty strict limitations, okay? And this will actually motivate why we use the virtual work method instead. So first of all, as you can see, we can only compute delta in the direction of the force that is applied. But B also moves down by delta y here, which we do not know and cannot solve using this method. In addition, the work energy method can get more difficult to apply as the loading patterns get more complex. So these are two pretty serious limitations that will motivate us to look for an alternative method, which is, in fact, the method of virtual work, which deals with these two limitations very well. By the way, this example is example 8.1 in the book, and you can refer to it to see how the equation is applied to get the value of delta x. But let's move on to the virtual work method, as this is what we'll be using from now on. And to do that, let's look at a very simple system. A single bar subjected to a load P, as you see here. And we're interested in computing the horizontal displacement at B, which we're calling big delta. F will be our member or bar force due to the externally applied load P. Small delta will be the elongation of that bar. And we know from before that delta is equal to F times L over EA. We also know from the work energy conservation principle that the external load will work linearly over the external displacement delta, as we see in the bottom left graph. So we get an area under this curve which is equal to 1/2 P times delta. And this we'll call the external real work, to differentiate it from virtual work, which we'll cover in a moment. Very same principles apply to the bar force. Internally, this will deform by delta as the force varies from 0 to F linearly. So the area under this curve is 1/2 F times little delta, and this we'll call the internal real work. Okay, so notice that we use WPE to denote the external real work. P denotes the real system because that's due to the external load P, and then the E denotes the external work, and we use WPI to denote the internal work. Again, P referring to the real system, I referring to internal. And we know, of course, from conservation of energy, purely from the same principle that we applied in the previous example, that WPE and WPI must be equal. Now we define a virtual system where we remove all applied load, so we remove P, and we apply instead a virtual load P sub V of any arbitrary value, but it has to be at the location and in the direction of the desired displacement that we're trying to calculate. So in this case, by coincidence, it goes at the same place in the same direction as P, but this is not true in general. Okay? So PV will be our virtual load of arbitrary magnitude. And generally when we say arbitrary magnitude, we'll just set that to 1, but this could be any number. 1 just makes calculations easier. F sub V will be the bar force due to the virtual load. Little delta sub v will be the elongation due to the virtual load, and big delta sub v will be the external displacement due to the virtual load. The principle of conservation of energy and work still applies here. Okay, so we get pretty much the same relationships, just using new values. Okay, so now we have a curve, a force displacement curve, PV versus delta V, but it's still a triangular shape. So that area there is 1/2 PV times delta V, and this we denote as WVE for external virtual work. Okay, so notice that V now denotes the virtual system, and similar thing on the other side, the area under the curve is equal to 1/2 FV times little delta V, and that we denote as WVI for internal virtual work. And again, due to conservation of energy, we know that the external virtual work and the internal virtual work are equal. Okay, so now here's where it gets interesting. With the virtual load in place, we apply the real loads on top of that. So notice how we have both PV and P being applied to our system. And from the principle of superposition, which says that for linear elastic systems, you can add the effects of both together to get the total effects, we know that the total bar force externally, P total, is equal to P plus PV. The total displacement delta total is equal to big delta plus delta V, and the total elongation is the sum of the elongations of both the virtual and the real system. Graphically, what this means is that we take the triangles of the real system and we just add them on top of the triangles for the virtual system. So as we apply P to the virtual system, the structure will displace further, again linearly, to the point delta total. And that will occur by a change of delta. Similarly, the final force will be P total, and the change in force will be P. And from the real system, we know that the area of that top triangle is WPE. Now we can follow a similar exercise with the internal loads to get the following graph, and we know that the area of that top triangle is WPI. Now here's the key observation. Again, by conservation of energy, the total area under these two triangles must be equal. That is, the total external work and the total internal work must be equal. That means that the area of the squares in between those triangles also must be equal. And we'll call those areas WQE and WQI. So we have W total external equal to W total internal, and by extension, WQE equal to WQI. And that's a real important relationship, because as you can see, WQE and WQI are determined by a product of virtual forces times real displacements. So for example, WQE is the product of PV, the virtual external force, times the real displacement delta, and WQI is equal to the virtual bar force FV times the real bar elongation little delta. This fact actually enables us to define the virtual forces that we want at the location and in the direction that we want in order to solve for the real displacements that we're interested in. So for any direction and displacement that we're interested in, we define a new virtual system with a virtual force at that location and in that direction. So we can generate as many equations as we want to solve for all the displacements that we want. And remember, that was a big limitation of the work energy method on its own. So in summary, we have, by conservation of energy, external virtual work equal to internal virtual work, external real work equal to internal real work, and total external work equal to total internal work. Which means that WQE is equal to WQI. In words, that relationship can be expressed as the work done by the virtual force PV on the real displacement produced by the real loads is equal to the work done by the bar forces produced by the virtual load on the elongations caused by the real forces. So that's a mouthful, but in terms of equations, we can express it in this way. Note that we define PV, so we know that one. We can calculate FV using our traditional methods. And also, by calculating the internal forces due to the real load, we can calculate small delta. So in other words, by knowing the F's, the real bar forces, we can calculate delta. And so we know those three quantities, so the one left to solve for is that external displacement delta. Now note that our example had a truss with only one bar, but in general, the internal work is due to the sum of the work done by all the individual bars. So we generalize this by adding a sum on the right side, where we add the internal work of each of those bars. So summing the virtual load on each of those bars with the real elongation of each of those bars. And like I said, that real elongation is the function of the real bar forces. So the elongation of bar I is going to be equal to the real force on that bar, right? Not the virtual force, but the real force times the original length of that bar times the Young's modulus and cross-sectional area of that bar. So again, let me emphasize this. This is the bar force due to P, the real system. Okay, so these only need to be calculated once on the real system, as we usually do for trusses. So that means our final equation is PV times big delta equal to the sum of I equal to 1 to M of the virtual bar forces times the real bar forces times the length of each of the bars over E and A. So the procedure for applying the virtual work method, which we will do in an example shortly, is first to solve for the bar forces Fi under the actual loads, the real system, then remove the loads and apply a unit load PV at the location and in the direction of the desired displacement. This we'll call our virtual system. Then we'll solve again using the same methodology for the virtual forces, which will be different from the real forces. And then finally we apply this equation to solve for the unknown displacement, big delta. So let's look at that in action. Here we have a simple truss, and we're asked to determine the vertical component of deflection at joint B, and we'll assume a uniform E and A for all the members. So we'd like to solve for this displacement, delta B. So this we'll call our real system over here. Then we'll define our virtual system over here where we've removed all the loads, and we'll apply the virtual loads accordingly. But to follow the procedure, we'll start with the real system. And so we would solve first for the reactions, and we would get the following. Then we would solve for each of the member forces. Notice that it's important to keep the signs here, okay, because the signs will be important in the overall sum. And these member forces in the real system, these will be our F sub i's, okay? Now we go to the virtual system. Since we're interested in finding the vertical displacement at point B, we apply our virtual load PV equal to 1 at that point in the direction of the displacement. And now we do the same procedure and solve for reactions and member forces. And these internal forces will be our FVI forces. All right, now that we have all the internal forces, we have everything we need to apply the virtual work equation. The easiest way to do this is to make a table where you keep track of the values. So I'll make a table and I'll define an index I. We have 5 members, so that index will go from 1 to 5. And I'll assign each of my members a number. So member AB will be 1, BC will be 2, AD will be 3, DB will be 4, and DC will be 5. Next, I'll note the length of that member, and then I will note the internal real forces and the internal virtual forces, F sub I and F sub VI. And then finally, I'll make a column for the denominator of that sum in the principle of virtual work. So Fi times Fvi times Li. Recall that the virtual work equation was PV times delta B in this case. So I'm simply making a column for this quantity here. So I'll go ahead and multiply horizontally. And once I've done that, I can sum all those values up. So my last row will be the sum, and that'll be equal to 798.3. All right, so now it's a very straightforward process to apply this equation. PV is equal to 1, so I can get rid of that. And so I have delta B equal to 1 over 200 times 10 to the 6 for GPA times 1 over 1200 times 10 to the negative 6, converting to meters. Okay, so this is GPA, this is meters. And in the numerator, we have our product. Okay, I need to be conscious of the units here. So my final product here was kilonewtons squared times meters, because my lengths were in meters. However, my virtual force is in kilonewtons, so I can divide out by that. And so I get kilonewtons times meter in the numerator, so I just multiply by 10 times 10 to the third Newton meters up here. And if I solve for that, I get 0.033 meters, or 3.3 millimeters, which is a reasonable displacement for a truss. Remember, trusses are fairly stiff structures, so we wouldn't expect them to displace all that much. So if you're getting displacements on the order of meters, it's usually an indication that probably something's off. So things should be generally on the order of millimeters. Now, one of the really powerful things about the method of virtual work is that it can be generalized even further to displacements or deformations due to effects other than loads. For example, changes in temperature. So a change in temperature in any one member will cause a deformation proportional to the temperature change, as well as the coefficient of thermal expansion. So in this case, our real system on the left doesn't have to be loaded at all. Let's say we just apply a constant temperature change in all members. That is enough to generate a deformation. So a positive temperature change will cause the members to elongate, and therefore we'll get something like this. And so let's say we would like to calculate the horizontal displacement of point D to D prime, which we can label as delta dx. In this case, we would find the real deformations due to the temperature change for all members in the real system, delta thermal I, and then we would define a virtual system to which we in fact apply a load in the direction and location of interest. Okay, so our virtual load of 1 is applied to D in the horizontal direction, and then simply we would calculate the virtual internal loads for each of the members, and then finally use the principle of virtual work to get the equation PV times big delta dx equal to sum over all the members of the virtual internal forces times the thermal elongations of the real system. And of course, PV simplifies to 1. The exact same procedure applies if there is some sort of fabrication error that causes some member of the truss to be shorter or longer than intended. Okay, this again will cause a deformation from the, let's say, the ideal structure. So to find what the deformation would be compared to the ideal structure, we can apply a very similar procedure. So in this case, let's say that member AD is longer than designed, meaning that delta AD is greater than 0. So in this case, because this is a determinate structure, the other members won't be loaded by this particular change in dimension. The structure simply will reorient itself to accommodate this member of a different dimension. So things can move around quite a bit. So it may look something like this, for example. Okay, now let's say we want to calculate the vertical deflection of C to C prime, that is delta Cy. Okay, again, exact same procedure. We have a real system in which we need the real displacements or deformations caused by the fabrication error. So we said that we would know delta AD, that would be specified, but because this is a determinate structure, the other members retain their original shape. They just move around to accommodate the new dimension. So delta AC, delta CD, delta AB, and delta BD will all be simply 0. In the virtual world, we apply a vertical load PV equal to 1, at C. Okay, this could also be up. That doesn't matter. You'll simply get a negative number if you guess the direction incorrectly. And so again, we would calculate the internal forces FVI and then apply the principle of virtual work. And because all deflections in the real system except for AD are equal to 0, this simplifies to the virtual force of member AD times the deformation of that member. Okay, one more cool thing you can do with virtual work, and that is account for support settlements. So it's very common in structures that are supported by soil or other movable foundations that supports can move and settle over time. And so virtual works gives us a tool to calculate the resulting loads and deflections due to support settlements at a particular location. So let's say in this case that our support B moves down, settles by a amount delta B or delta Bx. All right. Notice that I'm using big delta here because, again, this is an external displacement. All right. The structure will reconfigure itself around this displacement. But again, because this is a determinate structure, the reconfiguration won't actually load the members in any way. They'll simply just reconfigure themselves around this settlement. So we can say that the deformations of all the members are equal to 0. In other words, the support settlement doesn't actually apply any loads to the structure itself. And let's say we want to find the corresponding displacement at point D from this support settlement. Okay, we'll call that delta D. Should be pretty obvious that these two should be equal, but let's see what the principle of virtual work tells us. So this is our real system. Our virtual system, again, will include a load there at D, make that equal to 1. If we solve for the reactions, we'll see that the reaction By virtual is equal to 1. Now we apply the principle of virtual work, but there's something different about this problem. Notice that both delta D and delta B are external displacements, not internal displacements. So they must be multiplied by external forces, right, which would include the virtual force and the reaction at B. On top of that, they must go on the left side because that's where we include the external work, right? Remember, external work on the left equal internal work on the right. So our equation will look like this. Our virtual force applied at D times our real displacement at D plus our reaction, our virtual reaction at B times the external displacement at B. And this is equal to sum of the virtual forces times the real elongations, but we know that these are 0, so the right side of this equation is equal to 0. All right, and so if we plug in the values here, we would get PV equal to -1 in this case, because it's pointing down, times delta D plus BV equal to 1 times delta B equal to 0. Therefore, delta D is equal to delta B. Okay. Doesn't matter how you'd use the signs here as long as you're consistent, right? So you can choose either PV or BY to be negative, but just make sure that opposite forces have opposite signs. Okay, so in total summary, remember that the general statement for principle of virtual work is that external virtual work is equal to internal virtual work. So any forces and displacements that are external are going to go on the left side. Any forces or deformations that are internal are going to go on the right side. Right? In addition, it's always a product of virtual loads times real displacements. Right? So you should never be using, let's say, a real load times a virtual displacement. So overall, we have the equation that you see here, which can be used in general to solve any problem that has any combination of the effects that we just saw. It could be loaded externally, plus temperature changes, plus support elements, plus fabrication errors. Everything you can include in here. So you would get your applied virtual load times the displacement you're trying to calculate times any reactions, and we'll make sure that we specify here virtual reactions times real support settlements is equal to the sum of the internal forces from the virtual system times the deformations of the real system. Okay, and the deformations of the real system is where you can include all the different types of effects. So the effects of elongation due to forces, these are the real forces, the effects due to temperature changes, and the effects due to fabrication errors. So your task between now and next class is to try this general equation out on this truss, which has several effects being combined. So you have some changes in temperature in some members, you have one member that is too long and one member that is too short, and you have a support settlement. And we will work this in class on Thursday. So in summary, we've established that the principle of virtual work is a powerful, very general method for computing displacements due to a variety of causes, not just external loads. And it relies on creating a secondary virtual system in which we apply loads strategically to find the direction of the displacement that we want to calculate. So for every new displacement that you want to calculate, you need to define a new virtual system.